Hello, everyone, again. We will take it from where we left last time. We looked at the introduction of gauge theories, quantum electrodynamics, and QCD, and looked at the Feynman rules, and then looked at how the interactions are generated through the gauge principle. Then we also talked about how historically divergences were found when you want to go beyond the tree-level calculations. And we looked at a little example of how when divergences are found, then sometime to regularize them, you have to introduce an additional length scale or a mass scale. And then I think by the end, I didn't go through a couple of loop calculations, but I left them as an exercise just for you to go through the last 4 or 5 slides of the lecture. So I'll just assume that now we know how to do those calculations when there are divergences involved, and therefore some simple divergences with either one propagator in the denominator or 2 propagators in the denominator. Those results are known. As we saw in the explicit example with the electric potential, you end up having this gamma function and the poles of the gamma function through dimensional regularization, which allow us to separate the divergences. And the rest of the function, which would be the renormalized part after we choose which scheme to work with, will depend upon this the scale that we have to introduce. So I'll focus a bit on renormalization on quantum electrodynamics and QCD at the one loop level, and in particular talk about the renormalization constant, which is not really a renormalization constant because we will introduce another scale, a mass scale, and it will be a running coupling. Then just look at the status of whether we see that thing in the experiment or not, and then talk by the end, come back to QCD and see can we know something, how it evolves into the infrared, and just flash some recent results by paper, some papers who tell how it evolves into the non-perturbative region, which is actually quite problematic. And then later on in the next lecture, I will see that when we cannot do perturbation theory or when alpha is large, then what other possible ways you can have to solve your theory. And if there are similar kinds of solutions found or some new solutions emerge which are not observable in perturbation theory. Okay, so let's start. We had already seen last time the Lagrangian of quantum electrodynamics. So what I had missed last time was this gauge fixing term, but now I've added that. This is the same covariant derivative. Here are the interactions between the fermions and the photons. This part is the dynamics of the photon field. A mu is the gauge field. Here mu is the Lorentz index, but once it will disappear, it will appear as something else, the renormalization scale. So the second term is the gauge fixing term, and psi are the fermionic fields, which are the spinors. This is F mu nu explicitly, and just a reminder what is the covariant derivative in quantum electrodynamics. Okay. Now, as we had talked, we can do the calculation starting from this Lagrangian. We construct our Feynman rules and do the calculation. We can do the tree level calculations, but when we go beyond the tree level, they come out to be infinite, and we need to do the regularization, etc. Now, there is an advantage, and I can't go into all the details of that, when the theory is renormalizable, like quantum electrodynamics. There are some theories which are not renormalizable, others are. Quantum electrodynamics is a renormalizable theory, and that implies that we can add counter terms of the same form which were present in the original Lagrangian to work with the new Lagrangian, which will be called the bare Lagrangian. And if we start from that, then our predictions will, come out consistent with experiment at the theories which are not renormalizable is that every order you have to introduce new kind of terms, and therefore you don't have the handle on predictions anymore. So as the counter terms are of the same form as the original Lagrangian, it is straightforward to add them to the original one to get the modified Lagrangian whose coefficients will actually be infinite. So our starting Lagrangian will have quantities and entities which will be infinite by nature. And when we do the calculations, they will eventually be renormalized and we get the finite result for physical observables. So there is an original Lagrangian. We add the counter terms exactly of the sum, and we arrive at this bare Lagrangian. So I can write this bare Lagrangian. If I add the same terms, if there is a 1, I can add a c. There will be 1 plus c and 1 plus c. I can call it a d, and therefore it's the same thing. This gets simply multiplied. The same. So the new Lagrangian will look to have the same. So I can choose to write it as this, in which I say that every quantity has it's bare. Okay. Now, when I say explicitly, we can write this as it is simply that I explicitly write what was this and separate out the terms f mu nu, so that I can clearly see what are the fields. This is the a mu field. And here is the gauge parameter. We are working with covariant gauges, and then we have, here is a vertex, there is a charge, everything is bare. Now, quantities in this bare Lagrangian are connected to the renormalized quantities of the original Lagrangian through infinite multiplicative renormalization constants, okay? As I told you that if this was the original Lagrangian, you could add another term, and then this, what was already there, the 1 sitting here plus that something else, I call it Z3. But what I have added is an infinite quantity, and you'll see that these quantities, these renormalization constants are all infinite. So there is one constant sitting with each term. You don't have to keep track of all these terms. So this is what the renormalization constant is for the mass term, or for the mass term and the Lagrangian. This is for the interaction term. So this is what is renormalized is the vertex, and here is the interaction term. So this is what will renormalize the charge. Okay. So sorry, yeah. So this implies certain relationship between the bare and the renormalized quantities. You can write in 2 different ways, and therefore you connect these things with each other. So that connection, I hope I don't make it confusing. So I'm saying that the same bare Lagrangian, you can write it in 2 possible ways. One is in which I'm calling everything bare, every quantity which is arising there. And secondly, the original Lagrangian, I've just multiplied each of them, and that is what making it bare. So if these 2 Lagrangians are basically the same Lagrangians, then I have to be able to identify the terms with each other. Now, there can be some terms which are a bit messy, and sometimes some terms which are not messy, in the sense that, for example, if I look at this interaction term, there is a fermion field, but there is also a photon field, and there is also this charge. So there are 3 things which might be renormalized. No? So I will start looking at the terms which are not so messy, which means, for example, this term. This term has only photon field in it, okay, and nothing else. So I can make a comparison of this with this, and that will give me a handle of what to do with this Z3, how are they equal or not. And then another term which is more or less simple at the same level is this term. Yeah, this is not the interaction term. This is actually the kinetic term for the fermion field. Okay, so this only has fermion field in it. Okay? So this only has fermion field, and this only has fermion field. This allows me that you see this a mu b then should be related to this a mu field if there are 2 of these field here. So a square root of this I can absorb into the redefinition of this, and that will be called this a mu b. And another square root which is left, I can put it here, and therefore I can say this A mu B is nothing but Z3 square root times A mu. Okay? So Z3 is what renormalizes the photon field. Okay? Now then, this only has the fermion fields in it, and therefore I can look what is going here. So this a square root of this can be absorbed into this, and that is what makes it bare, and the other square root of this goes in here. And therefore, that's how, if the bare field is here, that's the renormalization constant, that's my renormalized field. So for much of the time, I will use this B explicitly for calling these fields the bare field, and when there is no index, it means that's the renormalized field. So I can use this without any ambiguity. And after I have done this, there are other things that I can go on to define. And what I define is that this gauge parameter will be renormalized, this charge will be renormalized, the mass will be renormalized, and I call corresponding. I use some notation which is appropriate to remember for the renormalization of other parameters which are there. So that's my definition. So I can start with the first form that I had for the bare parameters, and then I substitute this. Okay, then what do? I had this, all of this, and now I can use these definitions and also the result that I had obtained from here. So what will happen here? For example, this term which is here, I've defined that this C is related to the bare one through this ZXC. So I put here this ZXC and replace the site bare. Yeah. Okay. And this I know I have already computed that this is related to the original one through Z3 square root. And because it comes as a square, there is Z3 inverse, which is sitting here. And this Z6, which renormalized the whole Lagrangian, which is already sitting there. So I make this substitution, and all these things come here, one after the other in every term. I'm just explaining to you one term. Here there are more terms here. This is charge, this is this one field and the other field, and therefore there are more quantities which are sitting here. So once I do this, I've rewritten in this slide the same Lagrangian with all these things here. But on the other hand, I had written this bare Lagrangian as such. Okay, so it means that if this expression has to be equal to this expression, what I wanted to convey here is that not all these renormalization constants are independent of each other. Okay, this of course got absorbed into the definitions, but here, look, if you compare this, these can only be equal if all this product is 1. Okay, so this gives a relationship between these renormalization constant. And the same thing here. So this thing has all these terms coming here, and if this has to be equal to this, then all this product should be equal to 1. So this gives us relationship between the renormalization constants that tell us that they are not all independent, okay, from each other. So we make this identification, and that gives us these relationships. Okay, so Z6, which is the renormalization of the term, which is the gauge fixing term, is related, in fact, to the renormalization of the photon field and the renormalization of the gauge covariant parameter. And then there are these relationships. What we will find interesting and useful and actually quite simple in quantum electrodynamics is that for our purpose, we can just focus on this one. This ZE is what renormalizes the charge. Okay? And that is what our interest in see. So therefore, this Z, which is the charge renormalization, is related to how the photon field renormalizes, how the fermion field renormalizes, and how the vertex, the interaction gets renormalized. So it is related to all these quantities. But in quantum electrodynamics, amazing simplicities occur. And we'll see that this calculation of this is quite simple. Now, in general, these z's, because of the infinities, these are all infinite. And they will depend upon the scale that we had already discussed last time. Last time, in yesterday's example, this mu was an additional length scale that we introduced when we were calculating the electric potential, finite, regularized. But here it's a mass scale. We'll see how it arises. And it will also depend upon this epsilon. And as before, we'll see that all these renormalization constant, this I can be any of these, are infinitely large when we take this epsilon, when we take this regulated going to 0. So you don't need to look at all the definitions of all these fields, but this is there in the presentation. You can look at it. What for the time being, what is our interest is to see the renormalization constant associated with the electron field, with the photon field, or the electron-photon vertex. Okay, because these three are the ones which enter into the definition of something that gives us a different view of what charge is. Okay, because charge is not going to be a constant. We'll have to make it dependent upon a scale in exactly a manner similar to what we had seen before, that we have to introduce a scale from outside. Okay, and also that I'll be using this MS bar scheme. Okay, and in MS bar scheme, by experience, you will note that when we will do the calculations, all the renormalization constants, all 5, 6, 7, would have this form in perturbation theory. It will start, it's 1 because at the tree level, nothing needs to be renormalized, all is finite, so it is 1. And then we have one pole when we go to one loop. And then we go to 2 loop calculations, there will be one pole, and there will be other terms with the 2 poles, but we are not going to go into the complications of higher loops yet. And then there will be no other terms like constants or other things floating around. You'll see that MS bar scheme, they just make it look simple and compact. So we must define the renormalized coupling in such a way that it remains dimensionless. Remember that when we were doing this integral in 1 dimension, we say we'll do it in different dimensions, but then we have to keep the units of potential and electric field the same. So we had to multiply with some quantity which will make sure that happens. So that happens when we go and change the dimensions from 4 space-time dimension to slightly different. Then we have to introduce a multiplicative term that will take care of the dimensions. Okay, so there is a little bit of a homework. I'll not talk about action. The action is dimensionless, and there is an exponential and there is a Lagrangian. Their action is the integration of the Lagrangian density in d dimensions, and therefore it's like ddxl. Because it appears in the exponential, it has to be dimensionless quantity. So what I want to say is that d4x or ddx of the Lagrangian density should be dimensionless. Okay. So that means that the mass dimensions of the Lagrangian density is d. Okay? Because remember, if you have this ddx multiplying it, that integration, and ddx has mass dimension 1 over d, because the length dimensions are inversely proportional to the mass dimension for natural units. So 1 over d, and therefore the Lagrangian has to compensate that. Now the exercise that they're giving is that you start assuming that your ddx times the Lagrangian density is dimensionless, and therefore that will allow you to determine that in dimensions which are 4 minus 2 epsilon, how the dimensions of each of these field will be. So the photon field will no longer have this dimension 1, it will be 1 minus epsilon. The psi field, which is usually 3 over 2 mass dimensions, it will be 3 minus 2 minus epsilon. And this charge will have the dimensions, which will be epsilon. It's a simple little exercise like the one we did yesterday, and you can see that. So we have to take care, because now we see the charge is appearing dimensionful, which in natural units it shouldn't be. So to define dimensionless coupling, we need to introduce a parameter mu, which will be later called the renormalization scale. Now you may find that it's a strange way of defining this thing here. So we will define it as alpha over 4 pi, and it depends upon this scale, which is mu times minus 2 epsilon. I told you this E has the dimensions of epsilon, so E squared will have dimension E power 2 epsilon, And therefore, those mass dimensions have to be canceled. So I introduced this mu power minus 2 epsilon, and that cancel. Then I have introduced this strange number, which is this Euler constant, which was there in yesterday's calculations. And I said ms bar will take care of this. So if I had defined this from the beginning, it will just make life easier, and the expression is very simple. And then, but what you need to see is that imagine if you go back to 4 dimensions, you recuperate what you had or not. So imagine if you are in d dimensions as before, epsilon should be 0 because d is 4 minus 2 epsilon. And I put epsilon equal to 0, I get d equal to 4. So when epsilon is 0, this disappears here. When d is equal to 4, this is 4 over 2, 4 pi squared. And this is mu power minus 2 epsilon. This is 0. So it is e squared times 4 pi squared. But e squared over 4 pi is what we define alpha. And there's an addition factor of 4 pi here. So in 4 dimensions, it is exactly the same as the definition of alpha. Okay. Just going beyond how do you define it, it is quite simple to do it, although it looks a bit tedious, but it makes the expressions quite simple in MS bar scheme. And then we will just define this number sometime. We will not be dragging on all Z squareds. We will call, whenever Z squared is this, we'll call that Z alpha. Now, what I can also do is, because most of our calculation that we do on paper, we do keeping in mind of the bare quantities, and then we renormalize them. So, so I can invert them. I can take EB squared over 4 pi d over 2 on one side and all the rest on the other side, and just use this definition instead of Z squared, Z alpha. Here I sometimes show the dependence that all these renormal constants appear at the level of alpha, so they will depend upon alpha. So this is nothing tricky here. It's because when I'll be doing the calculation, I will be using these quantities, and then I will rewrite it in terms of the renormalization constant and alpha that depends upon mu. There is one complication that I will do, and I still have to fix it in my lectures, is that I keep changing notations. That is to keep you guys awake. Okay, if you're not, so sometimes I think I'll soon change the notation. When there is a B here, it's a bare quantity. When there is nothing there, that means it's renormalized. But soon I will have, when there is nothing written, it's a bare quantity. And when there is R written, that is renormalized. But anyway, it will make sense. So I hope you don't mind this. Okay. So this is here, I think this is the first warning of notation, that instead of using here bare quantities, I have put a 0 here. Even that will disappear eventually. So we'll just keep track of this. Once I'll fix all this, because I think I have combined different notes and that being lazy not to fix it. So these zeros are the bare quantities. And I told you about this Feynman rules, how the a massless electron propagator looks in terms of its Feynman rule. That's the rule for the photon propagator, and that we have for the vertex. These are quite harmless quantities when you do perturbation theory. But when we will see in the afternoon lecture, especially maybe of tomorrow, when we start doing non-perturbative QED, non-perturbative QCD, this vertex, for example, which appears, will no longer be simple gamma mu, because it has to contain itself the effects of all order perturbation theory, but not only all order perturbation theory, because there are some effects which will never be there, even if you were able to do all order perturbation theory. There are some effects which are completely non-perturbative, not seen in any order of expansion in perturbation theory. So this vertex will change its nature completely. It is actually written in terms of 12 basis vectors. And we have to know the coefficients of all of these non-perturbatively. It's, of course, a prohibitively difficult task, but that's what we will talk about, what we can do. And there are, of course, additional Feynman rules. I really don't want to go any of those because I'm not going to use it. You are experts on it. You know how to do it. You will do this. You've done it yesterday as homework, and you'll do some of this today as well after your social. So there are additional Feynman rules when they're loops. There is you multiply it by -1 and then trace whenever there is a fermion loop. And then you integrate over the momentum which run inside the loop. And there are properties of course, Dirac matrices when you take the traces. They're slightly different when you go to D dimension, and some people use slightly different starting rules, but it doesn't really matter so much. If you use this, these are good enough. So once you have all this technology, yes. Yes, there's also, yeah. Yeah, the whole, perturbation theory loops at any level, at any order of alpha, yes. Okay, so for example, this photon propagator, you can see has this structure, a complete, of all order photon propagator will have what will start with a bare propagator, and then there will be some self interactions, what is called the self energy. Photon polarization tensor will be here, and here all the diagrams are what you call one particle irreducible. If you don't remember, that's fine. If you know, that's fine as well. But I don't not talk about this. And then you can do this repeatedly, okay? And that will be the complete. In the end, if you go to infinite orders, because each time you pick up this photon Fermi or interaction, there's more charges coming in for each vertex, and therefore you go higher and higher order in perturbation theory. So this is this, and then you have this again propagator, and there is some this photon self energy, and then there will be another propagator. When we go to here, there are 3 bare propagators, and then there are 2 self energies here sitting over there, and you can keep doing it. One of the interesting things you can note, and that will especially be more relevant when we are studying the Schwinger-Dyson equations in the afternoon, is look at this thing. You will see that this term will become common at every order in perturbation theory after this one. You see, this is the same thing which appears here, and then it's in the repetition. In the third, it will be the same. Fourth, it will be the same. So this is something that you can take common out, but only from the second term onwards. And when you take this common out, this expansion will again start with d beta nu 0, and it will then have this common, and this will be then this term. So you can see that the rest of the notation after taking this common out is the same thing as the original propagator. So you can do this to write it more simply as d mu 0. You took this common out, and then it is the same propagator which were appearing here in. Okay. Now, maybe it's not so obvious at this point, but what you can see is that there are lots of indices running around here, because every photon propagator has two indices here. If you just take care a little bit, when you go home, take the indices, multiply this right side with d inverse. Okay, that d inverse will cancel with d inverse with some g factors or delta factors, whether you're in Minkowski or Euclidean space, and therefore that d will disappear here, and this will disappear here. And from the left side, you multiply it by d mu gamma 0 inverse. Okay, so only this thing will be left. And therefore, instead of this, you will have a d mu 0 inverse, and there will be inverse. It's just written a bit more compact way. Okay, indices will make probably your life a little bit more complicated, but I'm sure you can handle that. Then there is called word identities I was talking to you about. There is one of the word identities which tells us that these are non-perturbative identities, and I'm not going to prove that. There's this self-energy tensor when photon interacts with itself is transverse. That is what it wants to say is that it is perpendicular to the direction of motion of the photon. So when you contract it with one of any photon momentum p nu or p mu, it is 0, and that tells us that it is transverse in nature, because only this form, if I choose, then it is transverse, and you multiply with this or this, it is equal to 0. And therefore, it is pretty simple. It means if I look at this, what will be its structure? You see, already the structure of this, if you just forget this term for the time being, the rest is simply the inverse at the bare level. Okay, its level is this and this. But now, if I want to add this term, which will be the self-energy which is coming, subtracting here, knowing that this has the same structure as the first part of this structure, I can always add this, and nothing happens to this. Okay, this is something extremely important, especially in quantum electrodynamics, that this, if I call it the longitudinal part of the photon propagator, because it's not transverse, it never gets modified. It doesn't matter at what order in perturbation theory you go, it always remains the same. Okay. So if that was the inverse, I can see that d mu nu not the inverse becomes, you can write it like that. It's just, it is the inverse of the full d mu nu inverse, okay? And this part, the first part of this, because I'm saying that this is transfers to the photon propagator, I call it the coefficient of this, I sometimes call it dperp, okay? Perpendicular coefficient, okay? So this is dperp. Now there is one more thing you have to see a little bit, is if you have taken quantum field theory courses, you will know that the photon propagator is defined as the expectation value of the time-ordered product of the photon fields in the vacuum. Okay? So this d mu nu is actually proportional to 2 photon fields. Okay? And if it is proportional to 2 photon fields, then the bare propagator is renormalized to the is related to the renormalized propagator, but 2 renormalization constant which renormalize the field, okay, because it's proportional to the 2 fields. Now this I have again changed the notation. This is bare now, okay? I have not written here that it is B, but this is bare because now I'm calling this thing renormalized, okay? I would fix it at some point. Okay, and therefore you see that this d mu r, you can write it this. It's in terms of d mu nu bare Z3 inverse. There's Z3 inverse as well. I haven't put anything here for the XC thing, okay? But XC is actually XC bare. Okay. The only thing you need to remember is that the Ward identity tells you that this is never going to get modified. Okay. So what has to happen is that the renormalization constant which relates XC to XCR should exactly cancel this thing out so that it never gets changed. Okay, that means Z3 should be equal to ZXC, and that would also imply that Z6, which is the renormalization constant for the whole gauge fixing term, is equal to 1, because this thing is simply the ratio of these things. But anyway, we're not going to use it much either. So if you don't remember this thing, what is important is to calculate this one loop photon propagator. That's the only thing relevant for me to say something about the renormalization constant. I'll see why this is the only thing which is relevant. So this is how we define, this is the self energy. We have already talked about it. And this or what we need to calculate is whether this pi of p squared. Now I'm not going to do any integrations. I assume I have done the integrations, some integration yesterday, and see where the poles were and everything. I gave you, some exercise to do home. So I'll just flash quickly how you do the calculation. So you do the calculation using the Feynman rule. This minus here is for the fermion loop. Then there is a trace because there is a fermion loop. And then you start here, for example, this is vertex. And then there is a propagator. Then there is another vertex here. Then there is another propagator here. And then you have the Feynman rules. You put them together. Then you do the traceology. You take traces. Then you reorder your things. And you see that on the bottom, there are 2 propagators here. Okay. So sometime how you simplify this whole after taking the trace, either there will be 2 propagators in the denominator, or there will be 1 propagator. But we already knew yesterday how they are related related to the gamma function with a pole in d equal to 4 minus 2 epsilon. So when you do this traceology and just use those integrals which I showed you yesterday, you find that this is what you get. Okay. And your divergence is in just G11. I'll show you what this is. So this is the final result. Okay. And here it says p squared power minus epsilon. As I told you that now I'm not putting indices here. This is EB. This is the bare charge. But when it will be related to the renormalized charge, there will be a factor of mu power 2 epsilon. Okay. So that will get I'll collect it with this because this will become dimensionless. It will become p squared divided by mu squared power minus 2 epsilon.
Question. I think in Collins' book on renormalization, he says things like taking a trace doesn't commute with Dimreg. I don't know if it sounds familiar, but that always kind of confused me. I don't know if this is similar.
I don't know in what thing it will be valid. I haven't seen this, but I think that the traces which we are taking, that's how basically they're defined like this. that you take the trace and then you take the integration. But maybe if you do the integration and that take the traces, I don't know, it will be not, but we are doing the right way around. Yes. G11 is this. What I have done here is that I didn't show you the complete expression, but this G11 was written in the last presentation, and I take the value there and I have put it here. Okay, that G11, which was not rare, is this quantity, and this little G1 is this. Okay, and this term, which is this D minus 4 here, contains the pole. Okay, when D is equal to 4, this becomes a 0. So I will put here D is equal to 4 minus 2 epsilon, and that tells us that there is a 1 over epsilon pole here. And as I was telling you there, that there will be a mu squared cap factor coming from here. So it will become p square over mu square power minus epsilon. Okay, and then when epsilon going to 0, you can expand it in terms of logs. Okay, and that is where this log comes, log of minus p squared over mu squared. Okay. And this is related to d perp, the perpendicular, the transverse part of the coefficient of the transverse propagator. This 1 over 1 minus p squared is the same as 1 over 1 plus pi p squared at one loop level, because it's proportional to alpha. And we are working under the assumption that alpha is small. Therefore, 1 over 1 minus x is 1 plus x, plus higher terms, which will be absorbed at the higher orders. So this is the expression which becomes, and you see that as we had seen in earlier thing, there is one term which has this pole, 1 over epsilon. Then this epsilon times this terms is the finite piece. And there are terms which are proportional to epsilon squared, and this multiplied by this will be order epsilon, and that, you know, we can throw them away because they will be 0 when you take epsilon going to 0. And therefore now you can calculate your renormalized quantities, and there is a Z3 inverse sitting here, and that has to multiply it with this bare quantity. Again, there is the pole, this is the finite bit, and this is the part we can throw. Right? So this is how you define your denormalization constant. As I'm telling you, in MS bar scheme, you only add the term pole term, which will kill this pole. So you have to define this Z3 inverse as 1 plus alpha over 3 pi epsilon in order to kill this pole. Okay? Now, what happens is that you substitute here. Okay? You multiply 1 times 1 will give you 1. And this thing, when multiply this, is exactly opposite to this. Right? And that will cancel each other, and therefore it will kill the divergence. Now, you say that this multiplied by this will be different, but then this alpha is multiplying by this alpha, and that is alpha squared, and we are only looking at the renormalization of the order scale alpha. Okay, so we keeping ourselves alpha. It is all finite. And once you do this, this is the finite part of your photon propagator. But I'm not really so much worried about the finite part of the photon propagator at the moment, because I know that I'm going to calculate how the charge is renormalized. And therefore, what I'm more interested in the part which is infinite, which is the renormalization constant with this infinite pole. Okay. Now, there is something very interesting which happens in quantum electrodynamics. And that is that, you know, in principle, you have to calculate this one loop calculation for the electron propagator and one loop calculation for the photon fermion vertex. But you really don't need to do it for our purposes. Why do you not do it? Is that we have a word identity. There is a word Takahashi identity which connects the 3-point fermion photon vertex to the fermion propagator. And that's an exact relationship which is true non-perturbatively, which is true at any order in perturbation theory always. That means that it's true for the bare quantity, is true for the renormalized quantities and everything. Now, if you renormalize this, the factor which renormalize this is for Z2F and this is Z1F. And if this identity has to hold true, these two things have to be equal to each other. Z1F is the same thing. The same constant which renormalizes the fermion propagator is the one which renormalizes the vertex. Okay? So this Z1F is always equal to ZF2 for quantum electrodynamics. Okay? But this is only true in quantum electrodynamics. And remember, this is how, when were comparing the Lagrangians, what we saw is that the coupling, the renormalization constant for Z is in fact this. It's Z1F squared over Z2F squared multiplied by 1 over Z3. But if Z1F is equal to Z2F always, they will always cancel each other out, and we never have to do this calculation, at least for this purpose. And therefore, this Z alpha is only Z3 inverse. So if we are able to calculate one loop photon propagator, we actually know how our coupling will be renormalized. Okay. So Z alpha, which is nothing other than Z3 inverse, is 1 plus alpha over 3 pi epsilon. So this is, sometimes one, for the sake of convenience of notation, because most of the time the factors which arise are of this type, alpha over 4 pi epsilon, the pole terms. And so whatever left is what we call this Z1. So we forcefully put a 4 here and a 3 on the top. And this becomes Z1 is 4 over 3. This 4 will cancel with 4. In fact, we'll have 3. So this Z1 is 4 over 3. And this is the renormalization constant for the charge. The charge which couples electron to the photons. So I was telling you that there is a bare charge, and we had this definition in the MS bar scheme. Okay, how the bare charge, I've come back to the notation of before. EB is the bare charge, and it was related to the renormalized charge, which is alpha. Now I do a little bit of a trick, nothing else, because this new scale mu, and what I know is that our coupling will somehow depend upon this mu, and I want to see how does this coupling will depend upon this mass scale, because that's going to tell us that coupling is not a constant, but it runs with a momentum scale. Okay, so what I do is that everything that depends upon mu, I keep it on one side. So it is Z alpha, I keep it here, alpha and mu, and everything which doesn't depend on that, I take it on the other side, like 4 pi, I get here e power gamma epsilon, e power minus gamma epsilon. And I call this exponential of A, but I know that this side, it doesn't depend upon mu. Okay. Now I take the log of both sides. If I take the log of both sides, this becomes A. And this, of course, can be written as 2 epsilon log mu, and then plus log of alpha plus log of Z alpha, and where Z alpha is the renormalization constant, okay? And now I take the derivative with respect to log mu, and it will allow me is that the left side I have chosen, which doesn't depend upon mu, and therefore if I take the derivative of the left side, it's going to be 0, and the rest of it is simply what I can call 0 will be equal to 2 epsilon. I'm taking the derivative with respect to the log mu. Now, if many people would have seen this, and if you haven't seen it, there is something called, I'll come back to it, the significance of it later. We define as beta function of quantum electrodynamics, and it is defined as how this Z basically varies with this scale that we had introduced, mu scale. It's 1 over 2 d log Z alpha. So I can, at some point, I'll just substitute here. Sometime I'll do that for some of the arguments, and other time I'll not do it. So this thing which appears here, it is nothing but 2 time beta. What I have done is that simply kept it here and taken this on the other side. Therefore, there is a minus sign here. Now this thing, when you taking the differential, if you use this this sort of chain rule, then it is like that. If you take first, you'll take the derivative of this log of alpha, and then you take the derivative of alpha. And derivative of log alpha just simply gives me 1 over alpha, and this is d log alpha. This is minus 2 epsilon minus 2 beta. So this is something like that. Already I'm knowing somehow how alpha will be changing with the change of this scale that I have introduced. So this is the expression. What I have done here is this alpha was sitting here. I have just taken it onto the other side. And once I do this here, what you can see is that we know that beta of alpha will start at the order alpha, and therefore if it starts at order alpha multiplies alpha, that will be terms of order alpha squared, which at least for this part are not important to me at the moment. and therefore I can drop that. Now, so this is something that I know. On the other hand, I also have calculated Z alpha, okay, to one loop order. Remember, we have calculated this denormalization constant, and this was just 1 plus Z1 alpha or 4 pi epsilon. So it is log of 1 plus x, and I can again expand log of 1 plus x as in small powers of x, because x is small, alpha is small. So this is log of 1 plus x is just x plus x squared plus x cubed, but those are higher power in alpha. And therefore, if I take the derivative of this, I know that this is equal to this z1 over 4 pi epsilon derivative of this. So this is the differentiation. So now all this I can substitute back in the expression that we had previously written, and therefore this is this is d log z alpha. I substitute here what I have just calculated, and this epsilon cancel each other out, and what I finally found is what is the beta function or quantum electrodynamics, okay, at one loop level. So this is something really a very simple calculation that you can do it in an hour or a couple of hours. Okay. And therefore, it's another way of writing the same thing as I'm telling you that many times. Is you write alpha over 4 pi and see what is the coefficient, and you substitute back the value of z1, and then you know what is this beta 0, and beta 0 is minus 4 over 3. So it'll come back to this expression. For the time being, what I'm going to do is that I'm going to start again from this expression, and here directly, because there are logs involved and I want a non-perturbative expression, I just take the limit right away, epsilon going to 0, and when I take this is equal to this beta function. Now I can insert here the expansion of beta. Remember, this is what we had calculated: beta 0, alpha 4 pi. We know what is the value of beta 0. We just insert it here, and therefore what we have is in this expression, one loop expression, nothing but alpha, a constant that we have calculated from one loop perturbation theory, and it's running with mu. So something like that already telling you that this expression is telling you how this alpha is going to run with mu. Okay, with this scale, there's nothing else involved anymore. And this beta 0 came from the calculation of one loop photon propagator, because we didn't need the one loop fermion propagator or one loop fermion photon vertex. Okay, so this is the expression. This is what we write back in here. And what I can try to do is that, okay, what is the solution of this? One way to write, there is a derivative involved, and so that when you integrate it, there will be a constant coming, a constant of integration. But I just strangely divided into this part. This constant of integration here and here depends upon mu prime, another scale, but that's a constant. And therefore, I can write the solution of this thing as such. You can see that when you take the derivative with respect to d log mu on both sides, these things actually cancel because these do not depend upon this scale mu. This minus sign cancels with this, and therefore we get back the same thing. So this must be a solution of this with these constant here. We just written in a way that will be convenient for me to give meaning to what we are doing. So this last equation, what we do simply is that keep 4 pi over alpha mu prime on one side, take these on the other side, and write it as such. Putting these logs together, it becomes log mu prime over mu. So we are seeing somehow that this alpha will be varying as a power, as a log power with mu. Yes. Sorry? At the one loop level, yes. You can have a different, a constant, but it would be a constant which we'll have to fix somehow. And I'll come back to how we do it. That what experimentally we know what it is. So this is, once we reach here, we just invert, we can 1 over this, we can take. So this gets inverted and all this goes below 1. And here on this side, I can, if I top and bottom, I can multiply with alpha mu over 4 pi so that this becomes 1. And if I do this, then I have this expression alpha mu over 1 plus beta 0 alpha mu 4 pi. And this is a very well-known expression that you have for the running coupling of alpha mu. And we'll see what does it mean and where do we go from here. Okay. So now here we can calculate this value is very important. This is what we calculate from the photon propagator. And this comes out to be, it was minus 4/3. And this gives a little sign, negative sign, which is here. And that that changes the whole dynamics of a theory. The sign of this beta 0 is negative or positive. We will know that it's an asymptotically free theory or it's not an asymptotically free theory. Okay. And in fact, maybe it's a good time that I'll just mention briefly is that although we are talking about perturbation theory, and these signs are very important in perturbation theory, something very similar will also happen in non-perturbative dynamics. Something very similar. These signs, when we're talking about QCD, will very much depend upon the color charge, that is SU3 color factors, and the number of light quark flavors which are there, up and down and strange light flavors which are there. Depending upon how many quarks are there or how many colors are there, can change the sign of this quantity. Okay, so we happen to live in a world there are lots of colors and few flavors, and therefore the sign of this number for QCD is such that we have an asymptotically free theory. If we were living in a world with lots of fermion flavors, it will change. Okay, and not only this, and when we look at non-perturbative dynamics in the afternoon, we'll not see it today, but maybe tomorrow, is that this also happens in the infrared region. These color factors and these flavor factors, which determine the sign of this quantity for QCD, become very important when QCD becomes non-perturbative and where we observe hadrons. You know that QCD is a confining theory, and there is chiral symmetry breaking which takes place, and that gives us the whole dynamics of hadron physics. And that will change. If we happen to live in the world where there will be lots of flavors of quarks, especially light quark flavors, then we will reach a number where will the theory no longer be confined, because it will overcome the effect of anti-screening of gluons. And not only that, it will be asymptotically free, but quarks can run around everywhere because it will no longer be confined. Yes. Well, it will come because, the mass does not come in that, but you know that you can invoke masses depending upon the momentum scale that you are, the heavier quark will not produce, and they do not play anything because they completely become isolated from they become, how do you say, decoupled from the solutions. The color factor, basically. I mean, you see, you can have an SUN theory and instead of SU3, and that will determine what color you have. If you have SU3, yes, we have SU3 and we have a certain number of flavors. If you have SU3, the color factor is fixed because we are living in SU3. And then if you were living in a world with different number of flavors, then your dynamics can change. I'll come back to it and explain a little bit more in detail. In fact, I'll look at it several times in more detail. So it's just, talking a bit ahead. So this is just a different variable that I'm using because I'm going to use somebody else's figure. So wherever is mu prime, I call it Q0 squared and Q squared. So looking at this, you can tell us that one thing is that this find will be important. And secondly is that it tells that this running of this alpha is logarithmic. But it also tells you that for calculating this alpha, you should have an initial condition of thing that you have to know the charge at a different value of momentum to be able to evolve it to find it what it is at a different momentum. Okay? So one input has to come, and that comes from experiment. Experiment tells us what is the charge at a given scale. Once you know that, then you should be able to evolve it at a different place. And you might have heard it many times before that, as we had indicated before, the bare charge of electron, it gets actually screened by this virtual pairs around it. So, all the time in quantum field theory, and especially now we are doing perturbative QCD, we have loops. We have just seen that the photon gets divided into electron-positron pairs, and then they become photon again. And therefore, all these virtual particles are always surrounding this. And in fact, what you see the charge is the effective charge. And depending upon how far you are, if you are further away from it, it's more charged. If you go closer and closer, you see the bare charge. And in fact, if you were very close, you can see that you probably should be able to see an infinity of charge, logarithmic infinity. But we'll not get there so far. You may have questions, but I'll come to it in the next transparency. So you can see that all the quantities here are positive. So if Q square is higher than Q0 square, this quantity is less than 1, and therefore you'll see a higher charge because this quantity is less than 1. Now I will just use this, knowing that we are in one loop perturbation theory, this 1 over 1 minus alpha effective. Again, I can use this 1 minus x equal to 1 plus x to see how it will look like. This expansion looks a bit like that. Okay, 1 minus x that I've expanded. So imagine if we are looking at these interactions. What is happening is the following. Interestingly, I don't have to look at what happens to the vertex, or I don't have to look at what happens to the fermion propagator, because in QED, what is governing the running of coupling is basically the photon polarization, as I told you, Z3, because the other two cancel each other out. So somehow, what we can say is that all the effects which are coming here, in fact, can they result into some effective or not effective, but running coupling here. Okay, that's the running coupling effect which will be there, and that decreases when you have increased Q squared. Okay, so somehow if you use this expression that I've shown to you, if you are at very small Q, you have this 1 over 137 alpha that you have always used in your calculations, and you see that in the experiment. But if you go higher and higher in Q square, it goes larger from the expression that we have calculated. Now there is something people call the Landau pole, because if you take this result literally, there will be a point where it will become infinitely large because this diverges. There is 1 minus this factor when it becomes 0. The denominator will become 0 at some point, and that will make this alpha blow up, and that is what's called the Landau pole. But here, of course, I'll talk about a few things because they're very much related to what we are going to see exactly in the next lecture. Remember that when we do this calculation, it is all based upon, at every step of our calculation, on the fact that alpha is small. Okay. Now, when you say that this is alpha is becoming, and it can become infinitely large, and say, hold on, it can't become infinitely large because it depends upon the calculation which was done, assuming that alpha was small. Okay? So I really can't go there. As soon as I start approaching alpha around 1, my approximation breaks down. So all the perturbative calculation that I have is no longer valid. So if I'm saying that I'm going to hit the Landau pole, that's, I have to develop something else to see what really happens. Right? What we will see in the next lecture is that, let me assume what happens that if alpha of quantum electrodynamics goes close to 1. Can I really know something what happens when it flows to 1? Does the perturbation theory still hold or not? And we will find that, in fact, it doesn't. When alpha goes around 1 in quantum electrodynamics, 0.9, 0.95, suddenly you see that quantum electrodynamics generates some new solutions, which were never seen in perturbation theory. At any order in perturbation theory, they were not seen. But then it doesn't do that. It does it even a lot more different. There's something called anomalous dimensions in renormalization group equations that I didn't tell you. It's something like the power of the psi bar psi term, which tell you the mass anomalous dimensions. These non-perturbative effects changes the mass dimensions of the operators. And they change these operators in such way you remember that we have this Lagrangian in quantum electrodynamics, but we didn't have any 4 fermion interaction term. Like we had psi bar psi, which multiplies by the mass, but we could put psi bar psi power 4, and that's the 4 fermion interaction term, but that's not renormalizable, and that doesn't correspond to our perturbative QCD. But if we solve non-perturbative QED, the anomalous dimensions change in such a manner that our theory is no longer closed with just the Lagrangian that we had. We have to introduce new 4 fermion interaction terms to make it a closed theory. But then when you solve that theory, that again changes the dimension, then you have to introduce psi bar psi power 6. And then you don't know where it will stop, it will stop or not stop. So QED becomes a bit of a mess. Okay, and that I will talk about. But something interesting that we'll take the message is what happens to alpha when it becomes large. Here I'm just saying is that when non-perturbative X will set on, and it will happen much before you hit the Landau pole, and that is something that you have to see. There are some experimental figures here shown that I've seen them before. That experimentally, when you do the high energy experiment in quantum electrodynamics, you measure a cross section, and then you take an effective coupling and see what is the value of alpha, which is actually going to give you the same result that you see in the experiment. You make the comparison, you see what is the alpha at that momentum scale, and then you can try to see is that our one loop result is this line, and then there are experimental results which are computed from different physical processes, either the decays or the scattering cross sections, and from there you deduce what is your value of the coupling, and then you see that in fact it does seem that it's correct, that the alpha does seem to change with this thing, and in fact the alpha inverse is becoming small. That means alpha is increasing with energy, and when you are around the mass of the Z particle, then it is, I think, 128 alpha inverse. And for 193, it is 127. It changes very slowly because it is logarithmic. Okay, so the effects become clear much later. Now, again, for the rest of the time, I don't have much time. I think we, in principle, finished 1 minute ago. So just take me 2 minutes. I'm not going to present you. You see, we had already seen the QCD Lagrangian yesterday. I don't need to show you again. It's just that, again, I've changed notation. That doesn't change much. Okay, this G0, the bears and everything. So let me it's just the Lagrangian. I just have put these ghost terms and whatever. And again, this Feynman rules of QCD, we had already seen this, and I told you that this triple gluon vertex and this ghost gluon vertex, all this, it doesn't really matter. What is important, what matters is the same. Exactly the same kind of renormalization that I have to do here. Again, what I have to calculate is this alpha, okay? How the coupling runs. And the definition of this is exactly before. This Z alpha is related to the renormalization of the quark gluon vertex, the quark self energy, and the gluon. But the only problem is that in QCD, we are not lucky that these two things cancel. The word identity is a lot more complicated in QCD. These things don't calculate, so you have to calculate all three. Okay? So as a good professor, when it is simple, you do it and when it's complicated, you ask to do the students at home. So that's what I will ask you, that you see, in QED, we were lucky that Z gamma times ZQ is 1. In QCD, it doesn't happen. So you have to do, and there are many other things that don't happen. So I'll not tell you how these things, let me just go, where do I go? Okay. So in quantum electrodynamics, the product of this was 1. Okay, and that helped me that I didn't have to calculate any of them. Okay, but here in QCD, it's not like that. It's not only that, it becomes a lot more complicated. There is a color factor which comes here, and for QCD, it is 3. CA is equal to 3. And if for QCD, you want to go back to QED, this Casimir operator is actually 0 for quantum electrodynamics, so you get the result, which is 1. And this A is again change of notation. It is the gauge parameter here now. So it also depends upon the gauge. Okay, this is all. But the problem is that that this gauge dependence, in fact, will eventually disappear. Where will it disappear? Let me see. Anyway, it actually cancels out in the calculation of alpha. Okay. And eventually, this is what happened when you look at the beta function. This is for this is for QCD and this is for QED. Remember, we calculated QED. This is -4/3, and I was telling you this sign was important. The sign which is here. This is the sign which is there for beta z for QCD. Okay. This number is basically only half, 1/2. Okay. Don't worry about what else is there. These are number of flavors here. So you see that here, this number of colors, CA is equal to what, 3 here? So it's about 22/3. And flavors, it's 1/2 is 2/3. So it is much smaller, this number. Okay. So the sign of this is different from the sign of this in the world that we live in. So if I'm not remember, the number of flavors have to be more than 16.5, okay, in order for this sign positive to get reversed to give you a negative sign. And the sign of here determines that QCD is asymptotically free. So one of the messages that I want that, you know, we're going to stop here is for you to take is that that we live in a world of QCD in which the number of flavors is much less than 16.5, and that's why QCD is asymptotically free. And modern calculations also tell us that if the number of flavors is around 10 or 12, if it were, then we would be living in a theory which is not confining anymore. Okay, and that's very interesting that you see that this is an abelian theory. Flavors or quark or electrons were always there. It's the self-interaction which was not there in QED. So this is the abelian effect which causes screening. And if the screening becomes more dominant than anti-screening, then you have no asymptotic freedom and no confinement. Okay. Now, this you have already seen. I have done this. It's already, I just want to see you. Just want to see you this. So this is more like the experimental set, experimental results which come from different labs, different experiment, different processes happening. But there is, there's another thing we have to calculate in electrodynamics. This is the last slide that I have. That in electrodynamics, there is only one vertex available, which is the electron-photon vertex. Okay, but in QCD, there are many vertices, which is triple gluon vertex, which is 4 gluon vertex. There is ghost gluon vertex. And what you see is that this coupling G sits with all these vertices. Okay, so there are different ways of defining your coupling. The coupling will be can come from different renormalization constants. And what the Slavnov-Taylor or the Ward identities for QCD tell us that all those couplings are the same. They're equal to each other. But you can compute it any way that you want, using either one vertex or another vertex or different combinations of renormalization constants. Now, there is a calculation which is in shaded area blue that has been done by something called pinch technique with infrared, what is it called? Background field method. I don't want to go into it, something like Schwinger-Dyson equations. Effectively, this calculation is done with infrared dynamics of 2 quantities, gluon propagator and the ghost propagator and the ghost gluon vertex. Okay, that's it. So they do this alpha by computing this non-perturbatively without any reference to perturbation theory. Take some lattice results as well, which have been computed for the gluon and the ghost propagator, and using the techniques that they have developed. And because it is not related to any particular process, they call it process independent, because it's just looking how these propagators non-perturbatively behave. And the argument gave us that this alpha over pi goes to around 1 in the infrared region, which means that alpha is around 3, a value where you can't really use perturbation theory. Okay, so that's where we stop now. I'm done with perturbation theory. And now alpha has become larger. And the next hour, then we will talk about what happens when alpha is large. So one of the first things which we start is, let's forget about the Feynman diagrams because they're not going to help us. Okay. Then go back to the drawing board and see, do we have any alternative? Is there any other way? Unfortunately, I think many people will agree with me that we physicists, the only thing we know is how to do perturbation theory systematically. And whenever we go beyond that, it's quite a bit of a mess. So I will introduce first the mess, and then I will tell you, can we undo that mess and say something about non-perturbative dynamics in a different way, which is not there in perturbation theory. And again, I'll take some simple examples first, and then we will complicate things tomorrow.